Okay, so I'm a PhD student in the CREAF with a collaboration with the Autónoma University of Barcelona, and I will talk about advancing high-resolution drought monitoring with evaluation of remote sensing soil moisture product. Okay, so a bit of introduction. Drought is a natural climatic phenomenon with major economic and environmental impacts. It affects agriculture by increasing water scarcity and reducing crop yield. To quantify drought is not an easy task, so we need an indicator to calculate these deviating conditions. Research has shown that when we combine multiple data sets, it improves the detection and the monitoring of drought. So our main objective is to understand drought dynamics and vegetation impact. And to do that, we are trying to use ground data, remote sensing, as well as land use, land cover one. The main objective in this case is to compare remote sensing products of soil moisture across time scale to determine whether the soil moisture complements drought monitoring and they explore this relation with vegetation. A special focus is given on Ebro Basin. So Ebro Basin is located in the northeast of Spain. It's the second largest basin of the Iberian Peninsula. It's characterized by a semi-arid climate with annual precipitation from 300 to 450 millimeters of rain and average temperature for 14 to 16 Celsius Celsius. It's a strongly irrigated area with 551 reservoirs. So why this area was selected? This area shows high climatic variability and land use cover heterogeneity. It's bounded between four mountain ranges, two in the north, the Pyrenees and the Cantabrian, one in the south, the Iberian, as well as the Catalan mountains. So it shows steppe conditions. Moreover, it's a high there's a high agricultural margin of the area, with some areas generate more than 12 million euros from agriculture. Regarding the vegetation cover, it's mainly annual crops, 25%, followed by coniferous forest, 22%. The mid and the low area is highly irrigated. A bit of introduction more. Soil moisture, it shows high hydrological importance since 75% of the global precipitation infiltrates in the soil. From 2010, it's recognized as essential climate variable and has a very good use as an agricultural drought monitoring. So how can we measure soil moisture? So at first, we are trying to collect all the in situ stations that they are in the area from ISMN. And it seems that compared to the temperature one that I found, they're very sparse. So even though they offer very high resolution and frequent update, they're very sparse and often on long term since they belong to specific projects. So to solve this issue, we try to use remote sensing, mostly microwave satellite sensors, that they offer global coverage or weather monitoring, high penetration into soil, and reasonably high resolution monitoring. So at first, I tried to do a bit of review of the available remote sensing products. I only selected products that they offer 1 kilometer spatial resolution, and based on different factors that they vary either from temporal coverage, either from the sensor they based, or the continuity of the product. Okay, first we did a visual comparison of some of these products, and it was a bit tricky because trying to compare products that they have different values. So even though some of them, for example, the three of them come from Sentinel-1, they either have different values or they show a different results. So based on many parameters, we decide two. One from passive SMOS that is created by SARSAT, a common in Barcelona, that it's based on the physical-based relationship linking microwave to temperature, brightness, and soil moisture, relying on soil evaporate efficiency. This is a downscale product with a dispatch method, and it's less affected by vegetation compared to the Sentinel one in general, and also offers a longer time scale. While on the other hand, we have the Sentinel one from DPA, that it's a recently produced product from January this year. It uses a dual polarization algorithm that it estimates both soil moisture and surface roughness from a single snapshot of SAR. It offers high resolution, and it proves the vegetation correction compared to the Copernicus one. So a bit of methodology now. At first, we did some processing steps of grading all the products to 1 kilometer, projecting to UTM-30, aggregated to monthly means. Also, we masked some snow areas since on SMOS we had an issue with the results. And we compute soil moisture anomaly index that I will talk about later. And then we start doing a statistical analysis, comparing the temporal means and the standard deviation maps, compute the Pearson correlation, as well as temporal and spatial correlation of the monthly soil moisture anomalies. So just a small note on them. The soil moisture anomalies is a direct indicator from the typical soil moisture values that can capture the available water stress. And on the other hand, we have the SPI that we already calculated from ground stations. And it combines precipitation and a potential of transpiration from temperature. And we use this just for the comparison. So moving to some results. Here we have some maps from temporal mean. This is monthly from October 2019, that it was supposed to be a wet month. And it sees that the product, the Sentinel-1 and the SMOS, they look visually at least consistent. A bit more dry, it seems, the SMOS one. But on dry months, for example, in August 2023, they look very different. And SMOS seems to depict the dry condition that we can see in precipitation way better compared to the Sentinel one, that it doesn't even seem that that dry, sorry. We also did the same comparison with a soil moisture anomaly index that is more reliable. And it seems again that in the wet months, they have similar behavior corresponding to the SPI1, while on wet months, again, we can see that SMOS looks more similar than with SPI1 compared to the Sentinel DPA1, that it's drier, but not as much as the other ones. So we try to do a monthly correlation between the anomalies, and it seems that they're not that strong correlated. So they differ, but there's a good agreement on between them. But then we try also to see seasonality, since we saw these differences between the dry and the wet months. So we selected the driest and the wettest month based on the monthly mean precipitation. And we saw that actually on wet months, the products are more correlated compared to the dry ones. But this is a slightly important correlation. Yeah, and also we try to do one more analysis to explore the impact on vegetation. So we use the Korean land use land cover data. We reclassified it into 4 categories: annual crops, permanent crops, natural grassland, and wood vegetation. And then we try to enrich these data sets with drought events. As drought events, we assign the soil moisture anomalies that they're less than -1, and this value lasts more than 4 or 7 months. This time scale we selected since it represents lengthful harmful events for the area, for the agriculture, in order to identify if there's some areas that they repeatedly affected by drought, as well as to monitoring the vegetation impacts across the different land use land cover types. So here it's some of the results of the recurrent drought events. This is for the 4th month scale. And it seems that the DPA1 detects more events compared to the SMOS one. Probably has to do with that the SMOS one comes from a downscale product, and the close by areas look the same, while the SEN one capture localized condition better. And the image was the same in the 7-month scale. And regarding the vegetation impact, since we don't have distinct results, it seems that there's not that huge difference between the product and the vegetation, but it's still an exploration. So moving to conclusions. Sentinel-1 DPA captures the fine scale variability that SMOS misses due to coarse resolutions. In dry months, maps show different spatial distribution, with SMOS depicting dry condition more consistent with precipitation, while DPA highlights localized variability. These results are consistent with recent findings that these type of products are in good agreement, but the Sentinel-1 find localized events. What are the implications of all of this for the Open Earth Monitoring project? Sentinel-1 DPA could enhance operational monitoring by improving localized drought signals, while the SMOS provides a more robust large-scale patterns useful for basin-wide and longer-term analysis. And some future steps that we're planning to dive into is a cross-indicator detection to explore if some drought events appear only in soil moisture index Y or in SPI that comes from ground data, and what can explain these differences. Also, probably creating an early warning potential. Does the soil moisture from remote sensing provide earlier meteorological indices compared to the SPI ones, or do they capture drought with a time lag? And hopefully doing an integration of these data sets of how we can combine the local detail with a large-scale coverage. All of this trying to create a multi-scale view of agricultural drought. And regarding the Open Earth Monitoring project, we already caught up with of how to integrate this product to the map browser of Open Earth Monitoring. And the selected data that we can share for every basin is the Sentinel-1 DPA soil moisture anomalies for the whole period. Optionally, if it is interesting for someone, we can also share the soil moisture without the anomalies, like the original values. And for selected months, we could also share the SPI 1 or 3. That's all. Thank you for your time.
Okay, we have some time for questions before lunch. Just I will start. You said that two products are consistent, but you had a plot that shows that actually they are low correlated. What they are low correlated. The correlation coefficient was like less than 0.4.
I mean, it was only in the case of dry months, but in longer times.
Longer term, they are consistent. Okay. And Luca, questions? You've been mentioned, I think, on a slide, so you have to ask a question.
No, I don't say this. Yeah, I have already talked with them. We are in connection also with Jaime, who is leading the drought activities, and it would be nice to have this kind of case studies also in the hub. And probably the data sets that you are using, as you mentioned, it's 1 kilometer, the smallest one, but it's not really 1 kilometer. So in Sentinel-1, you can see a much better patterns. It would be very nice to me to if you compare the drought between SPEI and San Mosto, probably particularly in irrigated area, you should find probably drought in SPEI and not in San Mosto one. If yes, it would be good because it means that San Mosto can see irrigation, and it would be also very, very good for irrigation for agricultural practice. This is my. So if I have to suggest something to do in the next, it's something like this.
Yeah, I mean, we just finished this analysis, so we look forward to.
Then when you show the map, it's not fully clear to me the consistency, but I know that you have just started, so basically I don't want to.
Just one more question. Like I'm a big fan of MODIS LST. Is the land surface temperature? There's a daytime and nighttime, and you can see that the drought periods. You have a temperature in the night is much higher. Did you ever consider it's also 1 kilometer?
Yeah, no, because we were like on the drought part from the SPI, where we are using only in situ data, and we have 100-meter resolution. So this we will upscale to find the relation with the soil moisture one.